Okay, so I asked about the kinetic energy of 100 grams at 20 centimeters from the axis when the angular velocity is 2 revolutions per second. Same angular velocity we used to get the result 1.2 joules for the mass at the 40 centimeter position. Well, now the mass, we've either moved this mass to the 20 centimeter position or we've added another 100 gram mass at the 20 centimeter position. How's its kinetic energy going to compare to the kinetic energy of this mass? Well, one thing that we can easily see is that the circle this thing goes around has half the diameter, or half the radius if you wish, of the circle about which this one goes, which means it goes half as far per revolution. Now it's gone 2 revolutions per second, it's gone half as far in every revolution, that's gone half as fast, isn't it? So we don't need a bunch of formulas and equations to say that since it's moving around a circle of half the diameter, it moves half as far per revolution at the same number of revolutions per second, then it moves half as fast. Now if it moves half as fast, how does its kinetic energy compare? Well, kinetic energy is 1/2 mv squared. It's not half the kinetic energy, it's the square of half of the kinetic energy. What's the square of half? It's a fourth. So you have a fourth of the kinetic energy when you're here. So kinetic energy of equal masses doesn't increase linearly as you go from here to here. That's going to be important when we start talking about moment of inertia next time. Okay? We're probably going to talk about how to get moment of inertia in multivariable calculus, but you still won't know exactly what moment of inertia is. You're closer. Next week you'll know it all. Then what about a mass at 30 centimeters? Well, some people got that pretty quickly, at least somebody did. It's 3/4 as far along the beam, so you're moving along a circle with 3/4 of the radius compared to this one. So it's going to be moving 3/4 as fast, and the square of 3/4 is 9/16, so you're going to have 9/16 the kinetic energy. Okay, and then at 1/4 the distance, at 10 centimeters, if the mass is there, it's going to have just 1/16 of the kinetic energy of a mass out here. So if you had the 4 masses, 10, 20, 30, and 40 centimeters, you would have full kinetic energy here, just a little over half the kinetic energy at the 3/4 position, only 1/4 of the kinetic energy at the halfway position, and only 1/16 of that kinetic energy at the 1/4 of the way position. So you want to think about those proportionalities. Okay, one more question that relates to the kinetic energy of an entire beam, and this time the beam actually has mass. So we'll address that in a second.